So when you're looking at the e function, you can see that when you're looking at exponential functions, y equals a to the power of x, there is a point where the derivative coincides with the original function, and that happens when this limit formula is equal to 1. And that's where we find Euler's number, which is a, which is 2.7183 to 4 decimal places, which is also known as e. So from that, we can state that if y equals e to the power of x, then the derivative of e to the power of x is itself. So it's just e to the power of x again. So we'll do a few examples first. So we've got the first one here, which is differentiate y equals x cubed plus e to the power of x. So if we do our dy by dx, we end up with 3x squared, because we just do that polynomial as per normal, plus e to the power of x, because the derivative of e to the x is e to the x. The second one is y equals 5e to the power of x. So to do the derivative of this one, we just literally write it as 5e to the power of x, because the derivative of an exponential is the exponential function. This last one, though, it looks a little bit different, because if you remember back to our rules of differentiation, this one is a chain rule question, and it's because we've got e to the power of an actual function. So the first thing we need to do is identify these functions. So we've got our u function is x squared, take 5x plus 1, and our y function is e to the power of u. So then we do du by dx. Du by dx is 2x take 5, and dy by du is just e to the power of u. Again, derivative of the exponential is just the exponential. So then to get dy by dx, remember from our chain rule formula, we just multiply the two together. So we would have 2x take 5, and I'm just going to pop that in a bracket, and then have e to the power of u. But we know that u is e to the power of x squared take 5x plus 1. Oops, I'll just fix that up there. So that brings us to chain rule and the e function. So if we have y equals e to the power of f of x, then the derivative is the derivative of the power function, so the derivative of the inside function, multiplied by the original e function. And I've got a couple of examples here. So we have y equals e to the power of 5x take 2. So the first thing when we're doing the derivative, dy by dx, is working out what the derivative of that function in the power is. So the derivative of 5x take 2 is 5. So we bring that down to the front, and then we just multiply it by the original exponential function. So we get 5e to the power of 5x take away 2. Similar situation with the second example of y equals e to the power of x squared plus x. So we have dy by dx. Now we do the derivative of that function that's in the power. So that would be 2x plus 1. And I'm just going to pop it in a bracket again. And then we multiply that by e to the power of x squared plus x. So we have our derivative is 2x plus 1, e to the power of x squared plus x. Our next example is differentiate y equals x squared and then so x squared e to the x. So x squared multiplied by e to the x. You should notice and recognise that this is a product rule question, because we have two functions multiplied by one another. So our product rule when we do the derivative is the derivative of the first, which is 2x, times the second, e to the power of x, plus the derivative of the second, which is e to the power of x, multiplied by the first. So we have 2x e to the power of x plus e to the power of x, x squared. And if we wanted to, we could actually factor out some things there. So we can factor out x, because x is present in both terms, and we can also factor out e to the power of x. So we're left with 2 plus x in a bracket there. So you could factorise that if you needed to. The last example is looking at using calculus to show that there is only one stationary point on the curve of y equals e to the power of x divided by x, and we need to state what that point is. So the first thing you need to recognise is that because we've got a division of two functions, that we need to use the quotient rule. So I'm just writing that down there, the quotient rule. And remember, that's bottom d top minus top d bottom all over the bottom squared. So if we do dy by dx, we have its bottom d top, so x multiplied by the derivative of e to the x, which is just e to the x. Take away the top times the derivative of the bottom, which is just 1, all over the bottom squared. So then if I factor out e to the x at the top, we end up with x take away 1 in the brackets all over x squared. So our derivative here is e to the power of x, open brackets, x take 1, close bracket, over x squared. So we're trying to find a stationary point, and remember, a stationary point happens when the derivative is equal to 0. So I'm just going to write on here derivative equals to 0. If we were to put that into a Casio calculator, or you can work out what it would just be when x equals 1, the derivative is equal to 0, and that is our only answer. Therefore, it is the only stationary point. So we can write that down, only stationary point. And then all we need to do is sub in. So we say when x equals 1, we would sub it into the original equation. So e to the power of 1 over 1, which just gives us e. Therefore, the stationary point is at 1e. And you could have gone through and done a second derivative test to find whether it's a maximum or a minimum. And then you could state whether it was a minimum. This one does actually come out as a minimum, but to prove that, you could do a second derivative and work out whether it would be concave up or down, depending on whether the second derivative is positive or negative. So the points to remember when you're differentiating the e function is that the derivative of the e function is just itself. So all the other rules apply, so you still have to use product rule, quotient rule, and chain rule, but you just need to remember that the derivative of y equals e to the power of x is just e to the power of x.